In this lesson, we will look at how to create a computational attractor system using environmental data from Revit using Dynamo. As you can see in the background 3D preview of my Dynamo window, the orientation of the different panels are changing as my sun path in Revit updates. So as we drag this path, we can see those changes get reflected in the Dynamo background as well. To get started, I'm going to close my Dynamo document and my current Revit document to return to the Revit browser window. Since we will be using a sun path system, it is important to note that we will have to use a new project file. So we can just start a blank Revit project. I'll turn my sun path on by clicking on the sun icon located at the bottom left corner of the Revit viewport. We can go ahead and continue with the specified project location, date, and time. And we'll activate a 3D view. Upon activating the 3D view, we need to reactivate the sun settings in this view. The sun path is a visual representation of the sun's range of movement across the sky at a geographic location you specify within your project. Using the sun path's on-screen controls, the sun can be positioned to any point along its daily path. You may also modify the sun settings by clicking the Manage tab, navigating to Settings, Additional Settings, Sun Settings. While we're on the Manage tab, we'll navigate to Dynamo to launch a new workspace. And we'll go ahead and maximize Dynamo and click on New to start a new blank graph. To get started, I'm going to go ahead and double click for a code block node. As a reminder, a code block will allow us to quickly define a sequence that will let us define some X and Y coordinates to use downstream. To define the number sequence, I will use a start value of 0, ... We'll use a variable for count. Let's call this X count. And a variable for my increment. We'll call this spacing. Notice that the inputs are created on the fly as variables are used within our code block. Let's copy and paste the code block and change the X count to Y count. Utilizing the search field in the library, we will look for a double slider, which is also known as a number slider, and 2 integer sliders. And we'll reposition those to the left of the code blocks. Let's go ahead and rename the integer sliders X count and Y count so that it's easier to identify their associated use later. We can do that by right-clicking on the node and clicking on Rename Node. I will repeat this process for the number slider or double slider, giving it a new name of spacing. Now we could connect the output ports of the sliders into their corresponding input ports on the code blocks. Spacing to spacing, X count to X count, and we'll reposition this as well, and Y count to Y count. As you can see, the code blocks are now gray and not yellow because they're no longer in an error state because the inputs are fulfilled. Next, I will add a point by XY coordinates node to the workspace. We can do this by browsing the library. We'll go to Geometry, Points, Point by Coordinates. As you can see, there are 2 options. Let's use the option that simply has inputs for X and Y. Now we could connect the output of our code block nodes to the X and Y input ports of our point by coordinates node. In order to better visualize what this node is doing, let's change our X count, Y count, and spacing. As you can see, we simply have a diagonal list of points currently. This is because we need to change the lacing of the point by coordinates node. Once again, that can be done by right-clicking on the node, navigating to lacing, and in this case we'll switch it to cross product to generate a grid of points. It is also important to remember that you can use Ctrl B to navigate the background 3D preview and Ctrl B to switch back to the node workspace. Now as we change the X count or Y count, those changes will be displayed dynamically in the background 3D preview. Now we can use this collection of points to define a circle. Browsing to Geometry, Curves, Circle, we can see that we have a few different options, some of which we're familiar with. In our case, we're going to use by center point radius normal. This node provides an easy way to orient the circle using a directional constraint. Let's connect the output of our point by coordinates node to the center point. We can also add a code block by double-clicking on the canvas to define the radius of our circle. For now, let's use 1. By default, the orientation of the circle is defined for us. If we hover over the normal input, we can see that we have a value of a vector with the value 0, 0, 1, which is the z-axis, so it's currently pointing straight up. This z-axis defines the world up in Dynamo. Although I was successful in creating my circles, the goal is to create a field of diamonds. In this case, the circle by center point radius normal is really just an intermediate geometry that we're using to circumscribe a polygon around that geometry. If we browse to Geometry, Curves, Polygon, we can construct a regular polygon around that circle. Regular polygon requires a circle input and a number of sides to define. We'll plug in the circles into the circle input, and for number of sides, we would like to use 4 to make a diamond shape. In that case, we can double click for another code block, type in the number 4, and plug this output into the input for number of sides. And if we hold down Escape to navigate our background 3D preview, we can zoom in and position this to see those updates change dynamically. In order to better isolate the polygons that we just created, let's disable the preview for the circles that we're using. Once again, we can do this by right-clicking on the node, navigating to preview, and deselecting it. As you can see in our background 3D preview, our polygon preview has gaps. We would like to fill the gaps with additional polygons to form a continuous field of geometry. Let's take a look at how to accomplish this. To create a continuous grid of polygons, I will need to create a second grid of offset points and add them to my list of center points. My list of center points is currently plugging into the input port of the circle by center point radius normal node. To get started, let's select the first few nodes of our definition and move them over. And we'll go ahead and move the code blocks and the point by coordinates node up slightly. And we'll move the sliders over to the left. Now we can copy our code block nodes and our point by coordinates node down. We can achieve this by holding down Control after selecting the nodes, clicking on a node, and dragging down for a copy action. Notice that in order to be able to define an offset grid of points, I need to first understand that my spacing is establishing the distance between each point. In order to create a new point offset, I will need to be able to establish a relationship between the spacing and between the points. On our newly created code blocks, let's disconnect the spacing input ports. Now we need to make a slight modification to that spacing to offset these points. In order to define the offset amount, I will need to multiply the spacing value by 0.5 or 1/2. This will ensure that our second grid of points is offset by a value related to the global grid spacing. We can find the multiply node in the math library under operators. Multiply. This node will go to the left of the newly created code blocks. For our multiply node, the x input will be the spacing. For the y input, we want to use a value of 0.5. The easiest way to achieve this is double-click for a code block and type in 0.5. With the new code block created, we can use its output to fulfill the input of the y value of the multiply node. We can now plug the output of our multiply node into the spacing of our newly created code blocks. And as you can see, the background preview updates to show a newly created grid of points within the existing array of points that we created previously. Now that we have two grids of points, we need to create a new list to merge them together. This will allow us to send both sequences to the circle node simultaneously. To get started, I will disconnect the center point of the circle by center point radius normal node. And now we can combine these points into a list of points to create more circles. And we'll go ahead and move these nodes over to the right. In the library, we can search for list create. Clicking on list create in the library places it on the canvas. As you can see, this node has a different UI to it. It has a plus sign and a minus sign to be able to add inputs or remove them. In our case, we need two inputs. To fulfill these inputs, we'll connect the point by coordinates node, the first one, into item 0, and the second point by coordinates node into item 1. And now if we hover and pin, we'll notice that we have a newly created list that has two sublists of points. And we'll unpin that preview for now. Now that we have the list create fulfilled, we can use its output to fulfill the center point input of the circle by center point radius normal node. And we'll clean up the last couple nodes of this definition to better display what's going on. This basic definition automates the task of creating a grid of diamonds. Navigating the background 3D preview by holding down Escape and repositioning, we can see that as we make changes to any of the number values, those changes are reflected in the background dynamically. In this case, I now have triangles or quads, and I can modify their spacing. And the spacing is modified through a slider. So now as we change this value, it's updating for us. And we'll go ahead and change the X count to 11 and the spacing to 5. This allows us to accurately see how many panels we're currently creating. I would now like to replace the constant Z direction in this definition with a more dynamic input. If we go ahead and search in the library for sun, we'll see that we have several Revit related nodes in regards to sun settings. We're going to need the current sun settings and the sun direction node. So by clicking on those in the library, we've placed them both on the canvas. We'll position these side by side and over to the left of the circle by center point radius normal node. Now we can connect these nodes to fulfill the input of the sun direction. If we hover and pin, we can see that we have a value from it. And we can use this newly created vector to define the normal of our circle by center point radius normal node. And we'll plug that into normal. As you can see, in the background 3D preview, by navigating with holding down Escape, our panels have updated dynamically. They're now facing a direction that is not just straight up. They're facing the sun direction achieved by extracting that from Revit. Let's go ahead and make the background preview have a little more geometry to it to be able to easily see what's going on. We're going to go ahead and patch these polygons as a surface. If we go ahead and go to the library, to Geometry, Surfaces, Surface, we can find a node called by patch. This node will create a surface by patching together a closed curve. In our case, the closed curve is a polygon. With that node placed, let's drag it to the right side of the regular polygon node. Connecting the output of the regular polygon node into the surface by patch node results in a preview of surfaces in the background 3D preview. And once again, we can navigate that and see those changes reflected. Since this geometry is currently a very thin surface, we can also thicken the surface to make it represent more of a panel type of geometry. Once again in the library, if we scroll down, we can find that we have some nodes to thicken surfaces into a solid. In our case, we'll use the option that simply has a thickness and a surface input. With that node placed, we'll place it next to the surface by patch node and plug in the output of the surface by patch into the input of the surface.thicken node. Upon connecting that node, you'll notice in the background that our surface is thickened dynamically. The reason that they're thickening on demand is because the surface.thicken node has a default value of 1. Let's go ahead and use a code block to define this thickness to something a little bit thinner. Double click for a code block and we'll type in 0.1. And we'll plug that into that input. Now as you can see, we have solids in the background that can now react to the Revit sunsetting environment. Let's go ahead and tile our Dynamo window and Revit window side by side to see what's going on. With Revit and Dynamo open on the same window, we can now see how each environment reacts with one another. In order to have a little more display space in Dynamo, we can minimize the library by hovering on the right side and dragging it all the way down. And this allows us to be able to get a better preview of Dynamo. Additionally, we'll navigate to the background 3D preview by clicking on the icon in the upper right corner and zooming in. Now as we change the settings of the sun in Revit, we can see those changes updating in Dynamo dynamically. You can do this by dragging the sun settings in the 3D view or through Manage Settings, Sun Settings as well. Having these kind of live updates in Dynamo connected to Revit, this allows us to quickly understand the impact of the sun's position on our array of panels.